Okay, so now I'm going to talk to you about the second bit of unsupervised data mining. This is what I call community detection. So first, again, the general method here is you think of your data as turning into a graph. We sort of alluded to this a second ago. You make an affinity matrix and you get a graph from your data. And then once you have a graph, what often people want to do is find a kind of connected group of things in the graph. And there's a parameter that we're going to talk about a little bit, modularity, which is kind of how connected a cluster is. And then there's a variety of computational approaches. We're not going to go into the details of various algorithms for kind of efficiently finding this Louvain algorithm and so forth. We're not going to talk about them in detail, but that's a sort of outline of this. So now, and then related to this is once you have your graph of relationships, there's a whole variety of other methods that do what's called label propagation or diffusion distance. And this is a situation where if you have some form of label on your data, now this is more of a supervised thing, you can take the, you can propagate it over the graph. And people have different ways of doing this with like heat diffusion and so forth. There's a variety of different methods. I'm not going to go into this in detail. I just want to sort of say a little bit about this. And one of the people often use this, for instance, to find, do functional prediction of genes. They'll have a variety of genes that have different functions, and they'll make a network of them, and then they'll propagate their functions as labels on that network, using one of these, say, heat flow algorithms and so forth, label propagation algorithms. So they'll try to find driver genes in cancer and so forth. One of the methods there, I think, called HotNet, which is very much related to this kind of heat diffusion method. Now, another group of methods that take the affinity matrix between different data points and really think about them are what you might call spectral or dimensionality reduction methods. We're going to spend a deep dive into them in a second and talk about the sort of SVD and their SVD's friends. And these are some of the papers we're going to go over. But before we do the deep dive into that, I want to first just come back to talk about the modularity approach. Then we're going to go into the spectral thing. So let's talk about here, we're going to talk about how that modularity is calculated and then give you a specific example. So now we're starting a little bit more of a dive into these different methods. So for networks, there's this notion of modularity that was developed by this person, Newman. He developed it a number of years ago. And if you just kind of look at these two networks, here's a dolphin social network and a network of political books, I think, citations. You can kind of roughly just see by eye that just looking at the connections, you can kind of fractionate them into two groups, right? There's a sort of one group here, yellow, and one group here, blue, likewise here. And that's because there's more intragroup connection than intergroup connection. And mathematically, we can describe this by computing this number Q, which is kind of a modularity. And basically what we do here is we assign a module label, or this would be a cluster label or some sort of group label to two things. And then we can evaluate, once we have that labeling, how optimal it is. And the way we do that is we say, we compute this function whether two things, I and j, are in the same module. Okay, that's this delta function. Are they in the same module? If they're in the same module, we're going to count this. We're going to look at their connection, and we're going to look at the connection. Are they connected, or even the strength of their connection, if it's a non-binary thing, relative to the amount of connections we might expect. And this number here is kind of the expected number of connections between two nodes I and j. It's the expected number of edges, and it's related to the the degree of I and j. If they have very high degree, we might expect their thing kind of randomly, whereas a very low degree, we might not expect it. So we're going to compute this quantity and then weight it by if they're in the same thing, and then we're going to sum this over all the things. And what we'll see is that this quantity Q is very low if we have a very bad choice of labels. So if we put if we put, say we label the graph like this, reds and blues, and it's not labeled very much related to very coherent modules, we'll get a very low value. Whereas if we label the graph in a way that really reflects the clustering, this Q value becomes a maximum. And now I'm not going to describe this in detail, but there's a variety of different sort of search approaches where you imagine labeling and unlabeling the graph to try to find an optimum labeling, and that's a kind of you might say an optimum clustering. Now I'm going to show you practically how you might use that here. So I'm just going to tell you about a very bioinformatic application. We often look in bioinformatics at 3D organization of the genome. You probably know that the DNA, of course, is helical, but then that's coiled up more and then coiled up more, and it's a very complicated coiling of the genome. One experiment that we didn't talk about that much in the functional genomics section was called Hi-C, ascertains these connections. It cross-links the DNA and then sequences the things that are cross-linked together, and you can get essentially a contact matrix for all the things. And obviously, pieces of DNA that are very close in the line tend to be contacting, but there's also off diagonal things, and that shows bits of DNA that kind of wrap back on each other and connect. And people often want to find kind of groups of things that are highly kind of clustered together, and people use the term TAD, or topologically associated domains, for this. And one issue is to take this affinity matrix, which essentially instantiates some form of network, and find the modules in it. And so those are TADs, and those TADs, in terms of the genome organization, relate to something like this. So if you had a matrix like this, you found groups that are kind of associated, they might actually, in terms of the physical layout of the DNA, it might look something like that. Now you can do this by various, just looking for modularity. There's some small modifications that you'd have to do if you wanted to do this. One is you have to slightly change that expectation parameter in the modularity formula I showed you, take into account that things that are nearby in the chain tend to preferentially be nearby. But basically, you use, say, the Levine algorithm to find modules. So this is a little bit of a deep dive, not tremendously deep, but just to give you a sense of using modularity to find TADs, or clustered groups, in Hi-C.